under the supervision of Delbianco and Stronati. So I'm not the first one to point this out, but doing formal verification in a fast-paced development environment is quite hard. The typical workflow of having first a formal specification, then doing the implementation for it, and finally proving that the latter respects the former doesn't always work very well when the implementation is a quickly moving target. There's a lot of work, obviously, trying to address this, but we still fall short in many situations. In this talk, I'll walk you through our pragmatic approach to address this that relies on extracting specifications and using property-based testing. So was more or less the situation I found myself in when tasked with doing formal verification on the Tezos OCaml, the Tezos blockchain OCaml implementation. This is a very large code base consisting of around 1 million lines of code, although there's some duplication there, that uses a bunch of advanced OCaml features, such as monadic effects, GDTs, first-class functors, you name it. It's also quite dynamic. There are new versions of what we call the Tezos protocol, which is the core part of the implementation, every around 3 months. And it's also critical. As such, it has been subject to different verification approaches. In particular, I was tasked with doing verification of the incremental Merkle tree data structure, which is part of the sapling component of Tezos. This was a nice, or seemed a nice target for verification because it's quite a self-contained piece of code, only relying on some well-specified cryptographic primitives. And because it's a simple data structure with some clear invariants, though the fact that these are preserved by the implementation wasn't trivial. So specifically, an incremental Merkle tree, as the name might imply, is just a binary fixed height tree with 2 invariants. The first one, Merkle, the Merkle property, meaning that each node contains the hash of its children, and the incrementality property, meaning that leaf positions are filled up sequentially from left to right. So if we had to insert another element here, another leaf, it would have to be there. For the verification, we will focus mostly on how inserting elements into the tree preserves these 2 invariants. So this seemed like a very easy thing to verify. And I thought that until I took a look at the code that implements this in production. This is only a fragment of it. I don't want you to look at it much, but I'm just showing it to show that a full verification of this code would require modeling what we call the Tezos context, which is an explicitly passed state with a bunch of things, the monad that we use, which captures both error handling and LWT promises, the I/O effect caused by accessing and modifying the storage. And although it's not quite clear in the code, the tree itself is represented through a flat key value representation in this implementation. So this seemed like a lot of work. So instead, we decided to approach this considering a whole verification spectrum in which we wanted to move along. So we start having just a functional specification of the properties that we want to hold, and then we try to move to the right of the spectrum by refining the model and by proving parts of the specification over that model. So the key point here is that we wanted to get some value at every stage of this timeline, because in our setting, we don't really know up to which stage we will be able to get to. So we did that using property-based testing. Let's take a look at how we did it. First of all, we used F* for the specification and its OCaml extraction mechanism to extract both the implementation and the specification itself. So let's start from the first step of the workflow that I showed, in the case in which we only have a specification. Here, we can only extract the properties of this specification and the representation used in the model, because still that's all we have in the model. However, at this stage, we are already able to connect the production code using property-based testing. And we do that by following this diagram. Basically, we start with some data in the representation used in the production code, in our case, a 3T0, and we apply the function that we care to verify, getting some new data. Then we rely on a very simple simulation function that will take us from that data representation to the one used in the model. Here, getting two trees, and we finally check the specification properties over this data. So then we propose to continue working on the model until we are able to get to the point in which we can extract a prototype implementation from this model. With it, we'll do two things. First of all, we'll test the properties extracted from the specification over this prototype, as this verification might be only partial. And second, we propose to use this prototype as a reference implementation to do some simulation testing over the production code, bridging the production to the model. Finally, and if you get there, the final step of this workflow would be to have such a precise model that you could extract an implementation in order to replace the production code. Here we say full verification, but we recognize that in some cases it might still be useful to do some property-based testing over this code, as some parts of the model might still be axiomatized, or just because you want to check the trusted base that the previous talk mentioned. For example, the extraction mechanism in this case. So, but up until here, I've been talking about how we want to test the specification properties, and we want them to be automatically extracted from the specification itself. However, normally when you extract code from a dependently typed language like F star, the properties embedded in the types are normally erased. So how do we get them? Well, for this, we introduced a very lightweight specification extraction tool that will allow us to extract the pre and post conditions of an F star type signature as OCaml Boolean functions to use in testing. This, we say that it's extremely lightweight because it relies on the meta F star metaprogramming framework, meaning that our tool is just an F star tactic. So here we have a very simplified example in which on the left we have a function foo in F star, the signature, that has two preconditions. One, which is implicit in the type of the argument as a refinement, P1, and the second precondition, P2, in the explicitly in the requires clause of this function, and a postcondition Q. So here, by calling our tactic extract spec, we would get in the extracted OCaml code the pre and post condition predicates. It's important to note that this is that our tool is quite limited, as only trivially computable predicates are supported. But we believe that this is expressive enough in a lot of situations, like ours, in which the complexity is not really in the properties that we want to verify, but rather in some orthogonal aspects of the code. Also, it's important to note that although some of the QCheck boilerplate that we use for testing is automatically generated, the inputs still are provided by the user. The area of deriving generators is very interesting, but it was outside of the scope of this work. So let's go back to our real case scenario and see more or less what we did. So first, let's start by looking at the specification for this incremental Merkle tree or IMT. First, the type of the binary tree shouldn't surprise anyone. It's just a very simple binary tree. And then we have the type IMT for incremental Merkle trees, which is just a refinement of the previous type by the incremental Merkle properties. The second part of the specification consists of the type signature of this insert list function, which will insert a list of elements into the tree. Here we care about two properties. First, the fact that this function will indeed insert the elements that we are passed as an argument in the right positions, and that this function preserves the IMT invariance, which can be seen here as being implicit in the type of the argument and the returned value. So even here, even before writing the implementation of this function, we are already able to use our tool and extract the pre and post conditions as OCaml functions. Here we have the precondition for it, where we do some bound checks, and then we check the IMT invariance over the starting tree and some other argument coherence checks. And then the post condition, which will check these two invariants over the resulting tree T prime, and that the elements were inserted correctly. So with this, we are able to follow the diagram that I showed earlier in order to test the production code. So with very little effort, we are already able to use this specification to do some testing over the production code. And then we continued refining the model, as I said, until we were able to extract the prototype implementation from it. What's important here is that this prototype still abstracts away a lot of the implementation details from the original production code, like effects or optimizations. So it's still a loose model. So we were able to extract the code. We don't have to look at it too much, but the important points are that it's quite readable, especially after applying some OCaml format, which helps a lot. And also, it's very performant, or quite performant enough at least to be a very usable or useful reference implementation. So with this, we did the two things that we said that we would do. So testing the extracted properties on it, and we used it to as a reference to do some model checking over the production code, basically testing that this diagram commutes. So at this point, we went back to FTAR, finished proving all what we wanted about the model, giving us even more assurances over this right-hand side of this diagram, this reference implementation. But at this point, we were satisfied enough with the assurances that we got, and we thought that it probably wasn't worth the time to refine the model enough in order to replace the original implementation that I showed you. So this is where we decided to stop. So to recap, I presented our pragmatic incremental verification workflow through property-based testing that relies on a lightweight specification extraction tool based on the MetaFTAR framework, and we saw its application to a real-world code base. Thanks.